Hello students, uh, today we will discuss how to show a finite uh, algebraic structure, a group with the help of a composition table. The composition table is a type of square array. We write the elements in a matrix form which indicates all the possible products of the elements of the finite algebraic system. So we have this is our uh, composition table. This is a 1 2 entry of this composition square array. So it's this entry a first second a1 2 entry will be we got from uh, first entry of the first multiple left left element, first entry this, and from the left, first entry from the left and second entry from the top. Our ijth entry, ijth element of the composition table in the square array will get after multiplying the ith entry of the at the left to the jth entry at the top. So this is how we can find the different entries of this square array. The order of the element in the first column and first row must be same. Order means uh, this is first row A1, this will be A1, this is A2, this is A2, this is A3, this is A3, and so on. Means they will be the elements will be in the same order as in the row, the same order in the column, right? So here we write the composition, binary composition, which we are applying to the elements of the given algebraic system, right? And this is called row. Elements of the first row on which the composition table is applied is written in the first row, and similarly the elements of the same finite set in the same order as in the first row must be written in the first column, right? Now we'll multiply them. A1 with A1, we got A11. We'll apply this I throw A11 element of the composition table of the square array is the product of the first entry at the left and first entry at the top. Similarly, A12 of the composition table we got after multiplying the first entry at the left and second entry at the top, and so on. With the help of this, we will get this composition table complete. So after completion of the composition table, composition table, we will discuss whether whether the given algebraic system form with the under the given binary composition form a group or abelian group. We'll discuss from this composition table. So for this, now we will apply this composition table, the problem which we have already discussed. That is, show that the set this of consisting of -1 under the operation of usual multiplication of integers is an abelian group of order 2. So now given system is S consisting of -1 is a subset of integers, means elements of this set are integers. So elements of the set S will satisfy all the axioms satisfied by the set of integers. And the binary composition is usual multiplication of integers. That is multiplication. And now we have to show that this algebraic structure, this set consisting of minus 1, 1 under the usual multiplication, form a everything group. So for that we have to show all the five properties: closure, associated, existence of identity element, innocent, and commutative. First is, this is the composition table for this. This composition table minus 1. This is the composition, binary composition. We have written the elements of set S in a particular order, minus 1, 1. In the same order, we write the first column. Then the first row, first column, multiply minus 1 into minus 1, 1. Minus 1 into 1, minus 1. 1 into minus 1, minus 1. 1 into 1, 1. So this is the square array. With the help of this is a square array composition table. With the help of this, we'll discuss whether this will form a group or a. So for property. Now, for the discussion of all the 5 axioms, we'll use this composition table. The first is group. Now, all the elements of the composition table are the elements of S. This is minus 1, 1. You go to those elements of this is minus 1, 1. So, the elements of this, they are the elements of S. So, for the discussion, all the elements of the composition table are the elements of S. Then S is closed under the usual multiplication of integers. So, it implies closure property holds true. If all the elements of this composition table are the same as that of S, the given set, given algebraic system, then closure property holds true. Means we have in this table we have written all the possible, applied all the possible binary composition on the elements of S, and again we got the element belonging to S. Associative property. Since S is the set algebraic system which we are discussing this problem is a subset of integers, and integral multiplication is associative. We have read in the earlier lecture. So multiplication is associative in the set S, because all the elements minus 1 are also integers. So if we take A is 1, B is minus 1, C is minus 1, again A into B into C is equal to A B into C holds true. That's the existence of identity. Since second row is same as the first row, third row. Third row. In the composition table, element of third row are same as the first row. Therefore, this element will act as a left identity element for this algebraic system. And now, element of the second column are same as that of first column. Minus 1, 1, 1. Element of third column are same as the first column. Implies this one will act as a right identity element of S. So without this, one is the left identity and one the right identity. Therefore, combining first and second, we got A 1 into A is equal to A to 1 for all A of S. This is A is 1, 1 to 1 is equal to 1. If we suppose A is equal to 1, because S is only is a finite set, and this composition table is applicable only for the set finite set only. So if we have only two values, if we take A is equal to 1, 1 into 1 is equal to 1 is equal to 1. So again, if it is equal to minus 1, so 1 into minus 1 is equal to minus 1 to 1. So 1 will act as a identity element for the for this binary composition. One is now existence of inverse elements. In composition table, each row or column contains identity element. This row contains identity element, and this also contains identity element. This row identity element, this row identity element, or this column identity element, this column identity element. So for the discussion, Since in the composition table, each row or each column contains identity element 1 only one times. So the element left to 1 is the left inverse of the element above 1, right? Similarly, 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 the element above 1 is the right inverse of the element left to from this from this composition table. This is 1. This is 1. So this will act as a left inverse of this element. So this into this, a into b is equal to 1, and this b into uh, uh, this will act as a right derivative. Minus 1 to 1 is 1. So this act as a right inverse of this, and this will act as a left inverse of this. Similarly, 1 is here. This will act as a left inverse of this element, and this will act as a right inverse of this. The product of this and this is equal to 1. So a into b is equal to 1, and b into a is equal to 1. My a into b is equal to 1, and b into a is equal to 1. So this will act as element at the first column. The same column in which the identity element lies, left extreme element will act as left inverse of the top element. Similarly, extreme left element will act as a left inverse element of the element at the top of that. So the left inverse for this 1 to minus 1 is equal to minus 1. So this is equal to minus 1 into minus 1 1, 1 to 1 1. So 1 inverse of minus 1 is inverse of a into b is equal to 1, a into b is equal to 1, b into a is equal to 1, b into a is equal to 1. So inverse of minus 1 is minus 1. Inverse of from this, inverse of 1 is 1. So inverse both the elements, inverse of each element, minus 1 is also belongs to S, this also belongs to S. So inverse of every element of this finite set consisting of minus 1 are also elements of S. Therefore, inverse element exists for each element. Now, since the elements of the operation table are symmetric about the principal diagonal means now this is the principal diagonal. The minus 1 1 1 1 minus 1 1 minus 1. So element of this square array are symmetric about this meaning thereby this minus 1 to minus 1 1, so minus 1 into minus 1, a into b is equal to 1, b into a is equal to 1, therefore a into b is equal to b into a. Similarly, minus 1 to 1, minus 1 to minus 1 is equal to 1, and minus 1 to minus 1 to 1. So a into b is equal to b into a. So mean if the elements in the square array are symmetric about the principal diagonal, implies commutative property holds for the usual multiplication of integer in the set S. Hence, S will form a abelian. Now, we have discussed this with an example. Now, we'll have a complete discussion of this composition table. What conclusion we can draw? General conclusion from the composition table. As the algebraic system on which we apply the composition table, it must be finite, and this algebraic structure S with composition table, S with this composition, S with binary composition, we can draw this conclusion. If all the elements of the composition table are the elements of S, then S is closed under the binary composition table. S is closed to property. Second is if any row is same as the first row in the composition table, then the extreme left element in that row is called the left identity of element of S. Similarly, any column If element of any column are same as the element of first column, then the element at the top of that column is called the right identity element of that set. So left identity element exists, right identity element exists. So means identity element like this. Left identity you have found in the first step, second in the right in the set. So left and right identity element will be same. If then the identity element exists. This is right. Every if every row contains only one identity element, then the element headed by that row and first element of that row works as the left inverse of the element headed by that column in which the identity element lies. Similarly, element headed by the column is the right inverse of the element headed by the row. That is, if you go to the composition table of this so this is true. Now associated true. Now we can go to the composition table of this. Now this row contains the identity element. So this will act as a left inverse of this element, and this is the identity element containing this. This will act as a left inverse of this. Similarly, if you do column, this is one is here. This will act as a inverse of this. Similarly, this identity element is here. This will act as right inverse of this element. Right, this element. Now, fourth is if all the entries of a row or column are different, then left and right cancellation law holds true in S. Because there is a row or column are different means none of the element is repeated. None of the element here is repeated. They are different. They are different. They are different. They are means if this thing holds in the composition table, then we say that left as well as right cancellation law holds true. In square array, if the square array is symmetrical about the principal diagonal, then commutative law holds in S with respect to the given binary calculation. So let us discuss one more example. Show that the set G consisting of 1 omega square of cube root of unity form an infinite abelian group of order 3 under the multiplication of complex numbers. Now, given a G set consisting of 1 omega square, 1 omega square are the solution set of cube root of unity means solution set of x cube is equal to 1. So if they are the complex number, so we have read in this property sum of 1 plus omega square is equal to 0 and product of the roots is equal to 1. So we'll use this product of roots is equal to 1 in this composition table. Now we will show that this G consists of 1 omega square with binary convention usual multiplication complex number form a abelian. Now first we have formed a composition table for this. Composition is usual multiplication complex number. Elements of the set G are written 1 omega square. The same order first column 1 omega square. We multiplied them 1 into 1, 1 into omega 1 into omega square, omega into 1 omega into omega square, omega into omega square, omega cube is equal to 1, omega square into 1 omega square into omega cube, omega is equal to 1, omega square into omega 4 into omega cube into omega gives you 1 is equal to. So we have first formed this composition table by multiplying the elements of first column. Now from this composition table we conclude whether this will form a group abelian group or not. So first is Again, similar discussion as discussed in the first problem or second. Same discussion for every finite set to form a group or a group from the composition table. Now, close property. All the elements of the composition table are the elements of G. 1 omega omega square, 1 omega omega square. This composition table, they are elements of G. So G is closed under multiplication. Associative property. Since G is a subset of complex numbers, that is, elements of G are the complex numbers. We know that complex number multiplication is associative. Therefore, G is closed. The associative law holds in G also. Second is also true. Existence of identity element. Now, entitlement. Now, element of the first row are same as that of second row. First row are same as second row. Therefore, this will act as a left inverse of the elements of this. 1 into 1 is equal to this, 1 into omega is equal to omega, 1 into omega square is equal to omega square. Now similar discussion to a column. Element of the first column are same that of second column. Therefore, this element is a right identity element of this element of this. 1 into 1 is equal to 1, omega into 1 is equal to omega, omega square into 1 is equal to omega square. So, one is the left identity element and one is the right identity element. This one is left identity element, this one is right identity element. Therefore, identity element exists and exists in G. The next is existence of inverse element. Now, each row have different elements and identity element exists in row. This is the first row, it is here. In second row, it is here. In the third row, it is here. And similarly, in the column, in the first column, it is here. In second column, it is here. Third column, it is here. Right? So now this element, this is 1. So A into B is equal to 1. And so this will act as a left inverse of this one. And B into A is equal to 1. So this one act as a right inverse of this one, act as a right inverse of this one. Similarly, this one is here. So omega into omega square is equal to 1, omega square into omega is equal to 1. So this omega will act as a left inverse of this, and this omega square will act as a right inverse of this omega. Similarly, 1, this is 1. So this omega square into omega is equal to 1. So this omega square will act as a left inverse of this element, and this will act as a, this omega will act as a right inverse of this. So, very good. So now from this we can prove that inverse of, from this we can inverse A into B is equal to 1 is equal to B into A. Therefore, B is equal to B inverse is equal to B is equal to A inverse. So inverse of 1 is 1. Similarly, inverse of omega is equal to omega square. Inverse of omega square is equal to so all the elements. This one also belongs to omega. This omega square also belongs to G. This also belongs to G. Means inverse of each element in G exists. Since the elements of the composition table of G are symmetric about the principal diagonal, therefore commutative law holds true with respect to the multiple complex numbers. Hence, G form an ability. Now, similarly, you can discuss for this. In this problem, you are given, let A be a set. You are given this set, and you are given by some binary composition. This table has been formed. Now you have to discuss that it is a group or it is a group. So you have to discuss all the elements. You have to apply the general conclusion in the converse way to discuss whether this set G under the composition by which we got the elements of the square array form a group or a group. Similarly, you can discuss this problem also. Let G is a set A and B plus and root. This is a real number. This is a rational to rational. So Rational plus irrational. Irrational means this number is a real number. Now this is a real number. Rational plus irrational will be real number. Show that G, A and P are rational number means this set, this is a infinite set. Now you can't apply composition table to this. You can apply composition table only to the finite set. So show that G is a infinite abelian group with respect to addition composition defined by, I will define for all A plus B and root 2, C plus root 3 belongs to G. And how will you add them? A plus B and root 2 plus C plus and root 2 is equal to A plus C, real rational part plus rational part, and ABCD are rational number. You have to show that this is an infinite abelian group. You have to show all the five axioms to all the five axioms to this group. Thank